welcome everyone to the E3SM webinar. We're continuing our series with E3SM collaborators and ecosystem projects. And today we have TC talking about his early career DOE project. And please introduce Yoon.
Thank you, Mark. Yeah, I'm Yun Chen, the Earth System Modeling Group Leader at the PNNL. It's my great pleasure to introduce today's speaker, my colleague and close collaborator, TC Chakraborty. TC is an Earth scientist at the PNNL with interest in atmosphere-biosphere interactions. Before joining PNNL at 2021, TC finished his PhD from Yale University, where he studied aerosol climate interactions from a surface energy budget perspective. TC has a very broad research interest, including AI, machine learning, big data, and urban informatics to better understand cities and their complexities. His current work is mainly on improving urban representation in land models and examining extreme events over coastal cities. TC received the DOE Early Career Grant last year to improve urban representation in E3SM through Planetary-Scale data model integration. TC, floor is yours.
Thanks, Yun, for the introduction, and thanks, Mark, for asking me to present my work. Let me share my screen. I hope everyone can see my presentation, and let me know if you cannot. So I'll be talking about basically a planetary scale data model integration framework to resolve urban impacts across scales. And this is actually like part of my entire DOE early career proposal title, which also includes like and examine weather extremes over coastal US cities. It's a very long title, and I realized after the pre-application that I cannot change the title anymore. And PNNL at least has a lot of cool acronyms for their large projects, which I'm kind of thinking about getting an acronym for this at some point. So the work is still kind of very early. So I got the project funded in October, and I just got my 2 postdocs like a month back. So I will mostly be giving I will be focusing on the background and motivation of the work and talk about some of the research plans, including some very preliminary results. So starting with the background, so the physical process of urbanization is the replacement of natural land surfaces and also croplands with built-up structures. Examples are shown here over Las Vegas from satellite remote sensing, where you can see the impervious surface or built-up surface essentially expand over time. However, broadly, any change in natural land cover due to urban planning, which could include addition of urban green spaces, transition from native to non-native vegetation, could constitute urbanization. This is important because the world has rapidly urbanized over the last few decades. And these animations, and I'm hoping the animations are not very blocky, they show the change in built-up area by country over time. And there are also cases shown for large cities and the change in their urban extent over those same years. This is from 1992 to 2018. So this increase in urban extent accompanied by changes in surface properties due to urbanization, such as changes in thermal properties, morphological properties, and radiative properties, as well as anthropogenic activities within cities, such as HVAC systems or vehicular emissions, all impact weather and climate. Urbanization can impact weather and climate in various ways. This includes localized warming, which is known as the urban heat island effect, localized drying, known as the urban dry island, changes in cloud formation and precipitation over and downwind of cities, enhanced air pollution, particularly secondary air pollution, etc. Moreover, urban growth and densification may also lead to further feedbacks to the atmosphere, which are difficult to kind of resolve using current modeling frameworks. This brings us to the motivation of this work and kind of some of the limitations and uncertainties in the current urban representations in Earth system models and particularly in E3SM. So in Earth system models, urban areas are rarely represented. And part of the reason for that is traditionally urban areas were a very small fraction of the global land. And so it was assumed that there would be no impact on broader climate. The few urban representations in Earth system models use like a slab approach, where you have like a flat surface with the changes in radiative and thermal properties of impervious surfaces. And in the very few global models with actual urban morphology representation, they are far too simple. An example of that is in DOE's Energy Exascale Earth System Model, or E3SM, and this model, of course, comes from CLM. So the land component and the urban component comes from CLM 4.5. And no changes have been made in the urban component since it was incorporated, or in E3SM. So in this model, the entire urban subgrid is defined as this infinite canyon with roof, sunlit and shaded walls, and a canyon floor which is divided into impervious and pervious surfaces. All spatial variability within a subgrid for urban areas are defined by density classes. So these are like medium density, high density, and tall building district. Now, one big issue with this representation is that the surface constraints, such as radiative, thermal, and morphological parameters, are very poor. In E3SM, the entire world is divided into 33 regions. This is for the urban model, not like, I'm not talking about the general E3SM land model. The urban model is separate and has separate ways of representing surface constraints. So in these 33 regions, each region has a unique value for radiative, thermal, and morphological parameters. This means like the whole of India, Pakistan together has like the same value of albedo for all urban areas. The whole of China has the same albedo, same emissivity for all urban areas. But if you look at satellite derived estimates, and we are showing examples here for black sky albedo, which is the reflectivity of direct beam radiation, you can see a lot more spatial variability even within those 33, within each of those 33 regions from satellite information. So the underestimation of this variability would also strongly impact the cross-sample variability in urban climate. The other big issue with E3SM's urban model is that there is no vegetation within urban areas. The pervious part of the canyon floor is essentially treated like bare soil. But if you look at any real city, you have a lot more variability in not just morphological and radiative properties, but also the amount and properties of vegetation. Examples here are shown for New York, like parts of New York. So this is like a residential area, and this is near Central Park, etc. Another example here is for the Richland campus of PNNL, where you can see like this is technically within what you would call an urban area, but there is significant vegetation. And this is interesting because this kind of vegetation is not naturally supported by this climate because we are in an arid climate, but because of irrigation water, we can allow this much or dense forests to grow. So this is all kind of part of that urban land transition. And urban vegetation is very important because it modifies weather and climate. For instance, here we see the variability of monthly average surface urban heat island as a function of monthly averaged enhanced vegetation index from satellites. And they all show pretty consistent negative associations. Moreover, you cannot just take the rural vegetation and do some kind of area weighting to get the impact of a vegetated urban area, which is often done in the literature, because urban and rural vegetation are not identical. I already gave an example for Richland, which is in an arid climate where you can actually grow larger trees of very different species within the urban area through irrigation. But this is seen all over the world. The examples shown here are for Madrid and London, where you see changes or seasonal variability of the leaf area index and the solar induced fluorescence for urban and rural vegetation. And you can see there are large differences in the values for the urban and rural cases. Another big issue with E3SM's urban representation, and this is particularly relevant when we are doing long-term simulations, is that it is static. The E3SM land model uses an urban data set which is valid for around the year 2001. And in the next plot, okay, yeah, here you can see that that particular data set is the Jackson et al. 2010 data set. And when you compare that data set with other, present state-of-the-art urban land cover data sets, you can see there are large differences between them. Another interesting thing is that the low density class, even though it's in the original data set, is not used in the urban model. So what you see here as 2.02% is actually much less than 2.02%. It's something closer to, I think, 0.6%. And this data set is static for both historical and future simulations. But we know that historically urban areas have grown tremendously, and we also know that in the future it's going to grow a lot. And you can see examples here for 4 different urban projections for different SSP scenarios. There are uncertainties between them, but all of them show like significant urban growth from present day to the end of the century. And finally, the urban properties will also change. We already know that urban areas have greened significantly over the last 2 decades. There has been changes in albedo of urban areas due to cool roof strategies in particular cities. And urban morphology has also changed. Some, like cities in China, for instance, have grown vertically quite a bit. So that would affect wind flow as well as, and it also affects like the properties of those buildings, because taller buildings need different materials to for their structure. So here I define something which kind of combines this urban expansion with this change in urban properties over time, which I call urban evolution. And then finally, the final kind of issue with E3SM is related to coastal processes. So this is important because the majority of global urban population lives in coastal cities, and the urban coastal interactions can be very complex. An example is shown here for Chicago. This is based on a study we published through the Compass GLM project, where we are showing the lake to land gradient of different temperatures. So skin temperature, air temperature, and wet bulb globe temperature. And what we find is that even for daytime particularly, even though the direction of the variability is same, there are large differences in that gradient. And this is true for other variables such as wind, clouds, etc. The problem is that in most coarse grid models, you are not running these models at fine enough resolution to resolve urban areas. Examples here are shown for the NCEP-NCAR reanalysis, the ERA5 reanalysis, and the DAMED dataset. So the DAMED data is at 1 kilometer resolution. The black grids here show the typical resolution of a 1 degree E3SM simulation. One thing to note here with DAMET is that even though it's at 1 kilometer resolution, it doesn't actually resolve urban areas or the urban climate signal, because most of the data used for their simulation is not within cities. In E3SM, we can get urban signals through the subgrid structure. So each grid has different different subgrids, each responding to the atmospheric forcing. The problem, however, is that the model does not care where within the grid the subgrid is located. So the model doesn't care if the urban area or the urban subgrid is at the coast or inland. That has a huge impact on the interactions between coastal processes and the urban environment. So that brings us to the research plan. So my proposal and the project work is divided into 3 separate objectives, and each objective has like 2 to 3 subtasks. I'm going to focus on the main ones. There are some like smaller ones, and I just wanted to like avoid them just to save time. The first big task and objective is to improve the urban parameterization for E3SM. And there are 2 main ways I'm going to be doing this. First, I'm going to be explicitly representing urban vegetation and its interactions with climate within the model. And then secondly, I will produce a global spatially continuous urban surface data set. So this means that the pervious canyon within the urban model will now have grass and trees. And we are planning to use the WRF representation of vegetation. So there are a few cases where WRF has had urban vegetation included, including the BEP tree model. And actually, one of the postdocs who joined me worked on the BEP tree model during his PhD. So the plan is to incorporate that kind of structure into E3SM. And it shouldn't be too hard, just because WRF actually has a more complex urban representation, it being a multi-layer canopy model versus ELM being a single-layer canopy model. The second part is creating this global spatially explicit data set. Because as I mentioned earlier, that the entire surface property variability is divided into those 33 global regions. So this includes both creation of raw data set at high resolution, as well as then separating them into different urban facets, such as roofs, walls, roads, etc. So we will start by leveraging high resolution satellite derived global products, including products that we are developing with collaborators. An example here is shown for surface albedo at 10-meter resolution from Sentinel-2 imagery. And you can see examples that, the white roofs show higher albedo, which makes physical sense. And you can also kind of make out the road structures within the city. And also, like, a lot of vegetation would have a lower albedo because they're darker than the concrete around it. And then we can combine these 10-meter resolution estimates with kind of results for building footprints. An example here is shown for the Microsoft building footprint. So you can combine the building footprints with the 10-meter albedo to get average albedo for roofs for 1 kilometer pixels. Similarly, you can do that for roads using pixel level. So it basically requires first getting built up structures and then combining them with the building footprint images. And we actually already have these results. I've been working with one of my collaborators at UIUC, whose PhD student has been doing this work, and I'm helping with some of the workflow. So this is a list of the urban surface properties within E3SM. This includes like radiative properties. So for impervious road, pervious road, wall emissivity, roof emissivity, etc., and same for albedo. Morphological properties such as roof height, canyon height to width ratio, roof fraction, urban percentage, and pervious road fraction. And then the thermal properties. The thermal properties are the hardest to actually get spatially explicitly, so we are going to be leaving that for the future. But the radiative and morphological properties, we have already created this 1 kilometer data set. An example here is for Atlanta, Georgia, where I'm showing the default roof fraction and default roof albedo for medium density class. And as you might expect, there is no spatial variability at all. But here is the one at 1 kilometer resolution. So now you can see the spatially explicit roof fraction at 1 kilometer resolution over the whole city. Same for the roof albedo. So that's objective one. The second objective is to isolate the role of urban evolution on surface climate from continental to coastal scales. So this will be an extension of the first objective. So the first objective is focused on creating this kind of static data set, but one that's spatially continuous. The second objective will consider a spatio-temporally varying estimate of urban evolution. So that was the first part. Then we will develop high-resolution forcing over coastal areas, because there are differences in the coastal or the atmospheric properties as well over cities at that 1 kilometer resolution. And then we will be performing these land-only simulations to examine the urban impacts on surface climate across scales. So to develop these temporally varying urban parameters, the plan is to first start with our 1 kilometer present day estimate that we created from objective 1, and then map the Sentinel-2 based estimates with Landsat based estimates to get change over time from 1980 onwards. These will also be constrained against time series of actual urban extent. And here's an example for various different urban percentage data sets from various models. And for the future projections, we will constrain these with the future projections of urban land that I talked about earlier. So because there are multiple projections, we will have multiple possible urban future projection as well as their properties. And some of this work has again been done by some collaborators. So we have some examples, for instance, of change in urban properties and extent over time. This is an example of change in urban albedo from 1980 to 2020. And what we see is generally there has been a decrease in urban albedo over time, which means that more radiation is being absorbed by urban surfaces. The second part of this objective is to create this forcing data set along US coastlines. So we have to do this for both historical cases, which is easier because we do have like model simulations from like mesoscale models at almost 1 kilometer resolution, but it will be harder to do for future simulations. So the way we will do this is we will first run the E3SM coarse grid simulations for future scenarios, and then we will do physics constrained convolutional neural networks to capture this coastal gradient based on historical training data. And the importance here is the physics constraint part, because we plan to make sure that the mass and energy are, uh, you know, balanced for each of the grids based on the coarse grid simulation. And that brings us to the objective 3. And I think this is the one which is the most, I would say, um, open at the moment, because it depends on what kind of model development is done and what are the results from the first two cases. But the main focus here is to examine urban feedbacks to the atmosphere through coupled simulations, because the objective 2 is all land-only simulations. So here we will examine feedback from CONUS to coastal scales, and then understand the effect of urban impacts on coastal weather extremes. And the way to do this is, I mentioned earlier that we cannot really use coarse grid simulation to get the gradients around coastlines, because the ELM subgrid property is such that you don't really have a location of the subgrid within the broader grid. So we have to run regionally refined simulations. And this is already being done at pretty high resolution. So we are doing 3.25 kilometer resolution for ICOM. And the good thing is, from these 3.25 kilometer resolution, you can already see some spatial variability being captured. So for instance, for Washington, Baltimore, we see the relative humidity reduction within the city. So this is the urban dry island. But the plan is to do these simulations over 1 kilometer grid over the entire US coast by the end of the project, which will probably be like in 3 years. So we have some time to make sure that the computation is available to do these kinds of simulations. And then we will run perturbation simulations with different urban scenarios. So, past urbanization, present urbanization, urbanization with the existing urban properties, and then future urbanization, and understand how this urban expansion can affect extreme events such as droughts, heat waves, and storms. Again, this part I think is still the most open in terms of like what specific case studies we will do, but the plan is kind of moving from that 1 kilometer land only simulation to 1 kilometer coupled simulation for specific extremes. And with that, I come to an end of my presentation. So this, I got a huge amount of support while writing this proposal from PNNL, and there are multiple critical collaborations across labs with other institutions and even countries. Particularly, I plan, there's a lot of urban specific projects going on right now, and urban and coastal specific projects. The plan is to integrate with a lot of these other projects. This includes data sharing and model benchmarking between the Chicago and Baltimore urban integrated field labs, co-development of future urban evolution scenarios with IM3, as well as calibration of model improvements and understanding of coastal urban interactions with Compass GLM and the ICOM projects. The last two projects I have been a part of for a while. Thank you for your time, and let me know if you have any questions.
Okay, wonderful. Thank you.